Lesson 3, Laws of Addition and Multiplication. Definition: the addition law of probability states that the probability of that A or B will occur is the sum of the probabilities of A will happen and that B will happen minus the probability that both A and B will happen. That is, probability of A union B is equal to P of A plus P of B minus P of A intersection B. If A and B are disjoint, then probability of A intersection B is 0. So the formula becomes A union B equal to probability of A union B equal to P of A plus P of B. This is nothing but our fourth axiom. Theorem: if A and B are any two events of a sample space S, then probability of A union B equal to P of A plus P of B minus P of A intersection B. We have A union B equal to, so this is our A. A union B equal to this is A bar intersection B, this is A intersection B bar, and this portion is A intersection B. So A union B can be expressed as A union A bar intersection B. So these two are disjoint events. So probability of A union B equal to P of A plus P of A bar intersection B. Let us call it equation number 1. In the same diagram, we can express B as A intersection B union A bar intersection B. And also they are disjoint. Therefore, probability of B equal to probability of A intersection B plus probability of A bar intersection B, from which we can get probability of A bar intersection B as P of B minus P of A intersection B. Substituting 2 in 1, we get P of A union B equal to P of A plus P of B plus minus P of A intersection B. If A and B are any two events, then P of A union B equal to P of A plus P of B minus P of A intersection B. This rule can be extended to 3 or more events. For example, probability of A union B union C equal to P of A plus P of B plus P of C minus P of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. Problem: when drawing one card out of a deck of 52 playing cards, what is the probability of getting a hat or a face card? Here, face card means either king or queen or jack. Let us denote H and F for their events. Let H be the event of drawing a hat card and F be the event of drawing a face card. Since there are 13 hats and a total of 12 face cards, 3 from each shoot, which includes 3 face cards of hats. We have probability of H selecting a hat card, that is 13 by 52. Probability of face card, 12 by 52. Probability of face as well as hat, it is 3 by 52. So by addition theorem, probability of H union F equal to probability of H plus probability of F minus probability of H intersection F. 13 by 52 plus 12 by 52 minus 3 by 52. It is 22 divided by 52. We can simplify. that is 11 by 26. Next problem. Consider a random experiment of drawing a card from a pack of 52 playing cards. Let the probability set function P assign a probability of 1 by 52 of each of the 52 possible outcomes. Let A denote the collection of 13 hearts and B denote the collection of 4 kings. Compute P of A, P of B, P of A intersection B, P of A union B. So here A consists of as 2, 3, 4, 10, J, Q, K. So B equal to, in each suit we have king cards. So P of A equal to 13 hearts cards, 13 by 52. P of B equal to, there are 4 king cards, 4 by 52. P of A intersection B equal to, it is a king in heart card, it is 1 by 52. Now in the fourth subdivision, P of A union B, let us apply the addition theorem on probability P of A plus P of B minus P of A intersection B. So it is 13 by 52, 4 by 52 minus 1 by 52. It is 16 by 52. Simplifying, it is 4 by 30. Next problem. So let us recall the Demarcan's law. A bar union B bar equal to A intersection B bar. A bar intersection B bar equal to A union B bar. If A and B are any two events with the probability of A equal to 0.4, probability of B equal to 0.3, probability of A intersection B equal to 0.2, find the probability of the events A union B, A bar union B bar, A bar intersection B. So the first subdivision using addition theorem, P of A union B equal to P of A plus P of B minus P of A intersection B. So 0.4 plus 0.3 minus 0.2. Simplifying, we get 0.5. The second subdivision, let us find the probability of A bar union B bar. Applying Demarcan's law, it is probability of A intersection B complement. So we have already a formula for complementary statement. P of A bar equal to 1 minus P of A. So you can apply that formula 1 minus P of A intersection B. A intersection B probability is known as 0.2. So 1 minus 0.2 is 0.8. Here P equal to, we can express the event B as a union of two disjoint events. So this is our A, this is our B, this is A intersection B, this is A bar intersection B. So B can be written as A intersection B, A bar intersection B. And also they are disjoint. So axiom 4 implies P of B equal to P of A bar intersection B plus P of probability of A intersection B. Let us keep this term on one side. So the other side is P of B minus P of A intersection B. P of B value is 0.3. P of A intersection B value is 0.2. So the final answer for probability of A bar intersection B is 0.1. Next problem. If let A and B be two events such that P of A equal to 2 by 3, P of B equal to 5 by 6. So that the first one, probability of A union B is greater than or equal to 2 by 3. And second, 1 by 2 less than or equal to probability of A intersection B less than or equal to 5 by 6. We know that A is a subset of A union B. Therefore, probability of A is less than or equal to probability of A union B. So probability of A is given as a 2 by 3. So 2 by 3 is less than or equal to probability of A union B. So we get the required result. Probability of A union B is greater than or equal to 2 by 3. In the second part, we have two stages. A intersection B is a subset of B. So probability of A intersection B is less than or equal to probability of B. Of course, the probability of B is 5 by 6. So probability of A intersection B is less than or equal to 5 by 6. Let us call it equation number 1. For any set, any events, the probability is always less than or equal to 1. So probability of A intersection A union B is less than or equal to 1. Using addition theorem, P of A plus P of B minus P of A intersection B, I can rearrange this term. Bring this probability of A intersection B to the other side and bring that 1 to the left side. So P of A is 2 by 3, P of B is 5 by 6. Simplifying, we get 9 by 6. So 9 by 6 minus 1 or 3 by 2 minus 1 or 1 by 2. So 1 by 2 is less than or equal to probability of A intersection B. Let us call it as equation number 2. Combining 1 and 2, we get 1 by 2 less than or equal to probability of A intersection B less than or equal to 5 by 6. Conditional probability. If A and B are two events associated with the same sample space of a random experiment, then the conditional probability of the event A under the condition that the event B has occurred, written as probability of A given B, is given by probability of A intersection B is equal to A given B is equal to probability of A intersection B divided by P of B, provided P of B is not 0. Remark that A and B, the events associated with the sample space S of an experiment, then probability of S given B is equal to probability of B given B is equal to 1. Probability of E union F given B is equal to probability of E given B plus probability of F given B minus probability of E intersection F given B, where E and F are any two events associated with S. Just like the complementary formula in probability, P of A bar equal to 1 minus P of A. Here in conditional probability, we have probability of A bar given B is equal to 1 minus probability of A given B. Definition. The multiplication law of probability states that the probability that A and B occur is equal to probability that A occurs times the conditional probability that B occurs, given that we know A has already occurred. This rule can be written as probability of A intersection B equal to P of A into P of B given A. Also, we can write probability of A intersection B is equal to P of B into P of A given B. Example. Suppose that we draw two cards successfully and the cards are not replaced. If A be the event of selecting an as card first, it is not replaced, and B be the event of selecting again an as card. The card is not replaced is noted. So P of A equal to, initially there are 4 as cards out of 52. So P of A equal to 4 by 52. At the end of the first experiment, the card is not replaced. So now the number of as cards is only 3 and the total number of cards is reduced to 51. So P of B given A is equal to 3 by 51. Therefore, probability of A intersection B equal to P of A into P of B given A 4 by 52 into 3 by 51, so 12 by 1326, it leads to 0.0045. A fair die is rolled. Find the probability that the number rolled is a 5, given that it is odd. So it is a conditional probability related problem. The sample space S equal to 1, 2, 3, 4, 5, 6. Let A denote the event a 5 is rolled and B denote the event an odd number is rolled. So therefore A equal to singleton 5 and B equal to 135. So the conditional probability A given B is equal to P of A intersection B divided by P of B. So here A intersection B is singleton 5 intersection of the set 1, 3, 5. So it is noted that it is equal to singleton 5. And the probability of A intersection B is equal to 1 by 6. And B equal to 135. Therefore, probability of B equal to 3 by 6. So probability of A given B by the conditional probability formula P of A intersection B divided by P of B, that is 1 by 6 by 3 by 6. So the probability is 1 by 3. In a class, 40% of the students study math and science. 60% of students study math. What is the probability of a student studying science given he or she is already studying math? Here, let us denote M for math and S for science. So probability of M and S, that is M intersection S, is 40%, that is 0.40. And P of M equal to 0.60. Now probability of S given M by the conditional probability formula, it is probability of M intersection S slash P of M. It is 0.4 divided by 0.6, that is 2 by 3. So probability of S given M is 0.67. Two dice are thrown simultaneously. What is the probability that the number 3 has appeared at least once, given that the sum of the face value is 7? So the sample space S consists of all the numbers possible by the combination of two dice. That is, your sample space consists of 36 elements. S equal to 1, 1, 1, 2, 1, 6, 2, 1, 2, 2, 2, 6, 3, 4, 5, 6, 1, 6, 2, 6, 6. So totally we have 36 events. It A indicates a combination in which 3 has appeared at least once. Event B indicates the combination of the numbers for which the sum is 7. So if we list out the elements of A, at least 1, 3 is appeared. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. 1, 3, 2, 3, 4, 3, 5, 3, 6, 3. And event B includes 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So probability of A is 11 by 36. Probability of B is 6 by 36. That is cardinality of B by cardinality of S. A intersection B. is only 2 elements. So probability of A intersection B is 2 by 36. By conditional probability of A given B is equal to probability of A intersection B divided by P of B. So we get 2 by 6. On simplifying, we get 1 by 3. Two coins are tossed. Find the conditional probability that two heads will occur, given that at least one head occur. So when tossing two coins, the sample space includes 4 elements. S equal to head, tail, head, tail. Let A be the event of getting at least one head, and B be the event of getting two heads. So our A includes 3 elements: head, tail, head, and our B includes head. So A intersection B is head. Therefore, P of A is equal to 3 by 4. P of A intersection B is 1 by 4. Now the required probability of B given A is equal to probability of A intersection B divided by P of B. It is 1 by 4 divided by 3 by 4. We get 1 by 3. From a batch of 100 students, 100 items, of which 20 are defective. Exactly 2 items are chosen one at a time without replacement. Calculate the probabilities. The first item chosen is defective. Both items chosen are defective. The second item chosen is defective. So let us denote A be the event of choosing a defective item during first, and B be the event of choosing a defective item during second. So probability of A is equal to 20 divided by 100. The second subdivision, both items chosen are defective. So probability of A intersection B using product rule, multiplication rule, it is P of A into P of B given A. So it is 20 by 100, 19 by 99. So we simplify, we get 1 by 495. P of B, the second item chosen is defective. So we don't know anything about first item. It may be defective or good. So let us P of B, we can express B so this is my AB. I can denote this by A bar intersection B, this by A intersection B. Now I can write B equal to A intersection B union A bar intersection B. They are of course disjoint. So I can use fourth axiom, P of A intersection B plus P of A bar intersection B. A is defective, A bar is good. So let us apply the product rule, P of A into P of B given A plus P of A bar into P of B given A bar. So that will leads to 20 by 100, 19 by 99, 80 by 100, 20 by 99. That is 38 by 990, 160 by 980, totally 198 divided by 990. It is 1 by 5. A carriage mechanic keeps a box of good springs to use as replacements on customers' cars. The box contains 5 rings. A colleague, thinking that the springs are scrap, and he put 3 faulty springs into the box. So totally there are 5 good items and 3 faulty items. The mechanic picks up two springs out of the box while servicing a car. Find the probability that the first spring drawn is faulty. The second spring drawn is faulty. Let A be the event of choosing a defective spring during first and B be the event of choosing a defective spring during second. So probability of A equal to 3 by 8 and probability of B equal to B is nothing but union of the two disjoint events A intersection B and A bar intersection B. By axiom 4 we can write P of A intersection B plus P of A bar intersection B. Using multiplication rule, it becomes P of A into P of B given A is P of A bar into P of B given A bar. So replacing the values for P of A 3 by 8, P of B given A 2 by 7, P of A bar the complement is 5 by 8, P of B given A bar is 3 by 7. So we get 6 by 56, 15 by 56, 21 by 56. Simplify, we get 3 by 8. Let A denote the event student is female and B denote the event the student is French. In a class of 100 students, suppose 60 are French and suppose that 10 of the French students are females. Find the probability that if I pick a French student, it will be a girl. That is probability of A given B. Since 10 out of 100 students are both French and female, we have probability of A intersection B equal to 10 by 100 or 1 by 10. Also, 60 out of the 100 students are French. So probability of B equal to 60 by 100. So we get 6 by 10. So the required probability is probability of A given B is equal to probability of A intersection B divided by P of B 1 by 10 divided by 6 by 10, cancelling 10, we get 1 by 6. Thank you.